Hi everyone, so today we are going to see about a question which is related to the Carnot cycle and the Rankine cycle. Let's see the question first. The question states that the network output and the thermal efficiency of the Carnot and the Rankine cycle with the steam as the working fluid is to be calculated and compared. So in both cases, the steam will enter the turbine at 5 megapascal as the saturated vapor and the condenser pressure is 50 kilopascal. And in the Rankine cycle, the condenser exit state is the saturated liquid, and in the Carnot cycle, the boiler inlet state is the saturated liquid. And in both cases, draw the TS diagram. The question looks complicated, but let's recall back what is Rankine cycle and the Carnot cycle first. So basically, a steam power cycle plant, it has 4 components, which is the pump, boiler, turbine, and condenser. And for the ease of calculation, let us prepare the state, label the state first. So before the pump is the state 1, and then the pump will pump the water to state 2, and the boiler will boil the water, become the vapor at state 3, and finally the turbine will turn the vapor into the saturated liquid vapor mixture at state 4, and this cycle will continue. And if we translate this diagram into the TS diagram, for the Rankine cycle, it typically has this type of the cycle, which is that the process 1, 2 is an isentropic compression, and it is a change of the S is equal to 0 and a straight line. And from process 2, 3 is a constant pressure, the isentropic heat addition. So the pressure is constant, and the 3 will become a saturated vapor. And again, process 3, 4 is an isentropic expansion, and the entropy again is a constant, so again a straight line. And finally, from process 4 to 1 pass through the condenser, it is actually also the isentropic heat rejection, and the change of pressure is 0. So how about the Carnot cycle? The Carnot cycle is almost the same with the Rankine cycle, but it is a process 1, 2 is an adiabatic compression. Also, because the adiabatic is change of Q equals 0, the entropy will also equal to 0 change. So it is a straight line. And from process 2, 3, it is an isothermal expansion. So it expands at the same temperature, but it will have a same line at 2, 3. And from 3 to 4, again, is an adiabatic expansion. The change of entropy is 0. And from process 4 to 1 is constant temperature. So you can see it's, the cycle is a rectangular shape for a TS diagram. And now, let's recall back. For under the steady flow operation, the change of the kinetic energy, the potential energy, and the enthalpy is equal to the net Q minus net W. And if we say that there is no involved on the kinetic energy and the potential energy, so it will become the QE minus QR will plus with WE minus WR will equal to enthalpy of final state minus the enthalpy of initial state. And in this cycle, we need to assume that the pump and the turbine, they are isentropic because it's really isentropic, so the Q will equal to 0. And for the boiler and condenser part, we must assume do not involve any work, and W equal to 0. So with these two assumptions, we can say that the process 1, 2 across the pump, it has W equal to H2 minus H1 because the Q is already disappeared, eliminate. And since that it is a liquid state, when liquid is compressed, the change of the volume is constant. And we can say that H2 minus H1 will equal to V1 times P2 minus P1. And this because the work done is like this. Okay. And also process 2, 3 across the boiler, because no work, so the Q in will equal to H3 minus H2 because the boiler involved on the heat energy absorbed, so it's Q in. And from process 3 to 4 across the turbine, the negative W out will equal to H4 minus H3 because turbine will do the work right. So W out will eventually equal to H3 minus H4. And finally, the process 4 to 1 across the condenser, the negative Q out, because condenser need to remove the heat, become the liquid, so negative Q out equal to H4 minus H4. And finally, Q out equal to H2 minus H1. So this 4 process is the most very important for us to find the network output, because we know that Q in will equal to H3 minus H2, and Q out equal to H4 minus H1. So we also know that the network output equal to Q in minus Q out. So from this equation we find the network output, and the efficiency, the thermal efficiency will equal to 1 minus Q in over Q out. because it entered the turbine, we know that it is state 3. So state 3, the 5 megapascal and saturated vapor. And it's easier for us to draw a TS diagram so we know what actually is how it looks like. And since we know that it's an asymptotic process from 3 to 4, we should know that it is a straight line, and the state 4 is a saturated liquid vapor mixture. And it also tells us that the condenser acid state is a saturated liquid and condenser pressure is 50 kilopascal. So we can label the diagram in this way, which is 50 kilopascal and also the state 4. Okay, because we say that it's leave the condenser, so it is state 1, pass through the state 1, also the state 1 is a saturated liquid. Okay, how do we solve the problem now? So since we already know that 4 to 1 is isobaric, so P1 will equal to P4 equal to 50 kilopascal. And we know that Q in equal to H3 minus H2 and Q out equal to H4 minus H1. So from the information of the 5 megapascal and the saturated vapor at state 3, we should be able to find the enthalpy 3, H3. But how do we find H2? This we need to use the process of 1, 2. We know that the work input by the pump is equal to H2 minus H1, and we also know that H2 minus H1 equal to V1 times P2 minus P1 from the formula just now. And we already know that at the state 1 is a saturated liquid at 50 kilopascal, so H2 will equal to V1 times P2 minus P1 plus H1. Using this value, we will find the H2. And from the process of H4 and H1, we also already find the H1 from the information just now. But how to find H4? Since just now you said that it's an isentropic process, so entropy of 3 will equal to entropy of 4. And from the 5 megapascal and the saturated vapor, we already find out the entropy 3 S3, and we know that the value is same as the S4. And because it's a saturated liquid vapor mixture, so we need to find the entropy of the liquid and the vapor at the 50 kilopascal, and using the formula to find the mixture, the quality of the mixture, and we find out the X value. And we know that H4 will equal to HF plus the quality times the HFG. So using this value, we can find out H4 too. And after find out this value, of course, we can find the answer already. So let's see if we find out all the value already. We use the method we learned just now. We can get the P3, the enthalpy1. Because it asks us to plot the TS diagram, so we also need to find the temperature 3, the value. So we already know the enthalpy1 will equal to 340.54 kJ per kilogram from the table Air4 and Air5. And also we know that H3 using the formula just now and the value that we find, it will become 345.64 kJ per kilogram, meaning that enthalpy 3 is 2794.2 kJ per kilogram. And finally, the enthalpy 4 will equal to 2069.07 kJ per kilogram. So find out this H1, H2, H3, and H4, meaning that Q in will equal to 2794.2 minus the 345.64, and we get the value 2448.56 kJ per kilogram. And for the Q out, we know that it's H4 minus H1, so it equal to 1728.53 kJ per kilogram. And you know the net work is equal to Q in minus Q out, so you get this value 700.03 kJ per kilogram. And the thermal efficiency using the formula we get 0.294. And after you find all the value of the temperature, the entropy, we plot the TS diagram from state 1, state 2, state 3, and state 4. So we will get this graph. Now solve for the Rankine cycle. Now we go to the Carnot cycle case. Since we already know that the Carnot cycle case, the state 3 and state 4 is exactly the same with the Rankine cycle. So we don't have to find again, we just have to use the value of the enthalpy 3 and enthalpy 4 of the Rankine cycle. Because it's a 50 kilopascal, same condenser pressure and the isentropic. Okay. So we just have to find the H2 and H1. If H2 is already give us to tell us that for the Carnot cycle case, the boiler inlet state is as saturated liquid. So using the information of the saturated liquid and 5 megapascal, since it's P2 equal to P3, the isobaric heat addition, So we find out the hash2 value, and to find the hash1, we need to apply the knowledge, which is the isentropic, same S2 will equal to S1. So when we find out the entropy of two value, and we know that P4, the pressure 4, which is the 50 kilopascal equal to P1, and we already know that the entropy value, since we use the formula again of S equal to S1 minus SF minus S3 minus SF, and find out the quality, we know that the enthalpy will equal to HF plus X HFG, this value, and we find out enthalpy 1. So solve the problem, hash4 we get the value, hash3 we get the value, and the Q in equal to hash3 minus hash2, and Q out equal to hash4 minus hash1. So we find out that enthalpy 2 equal to 1154.5 kJ per kilogram, and enthalpy 1, we find out that the quality is 0.28, and enthalpy 1 will thus equal to, apply the formula, will 985.86 kJ per kilogram. And Q in, hash3 minus hash2 equal to 1639.7 kJ per kilogram, and Q out will equal to 1083.21 kJ per kilogram. So we can find the network output using the formula 556.49 kJ per kilogram, and the efficiency will equal 0.339, and the TS diagram, since it's a rectangle, and when we put all the value inside the 1, 2, 3, 4, we will get a diagram like this. So that's all for our standard question part, and now we should move on to the application part. Let's see how we can make this question more interesting and more challenging. So the question is like this. The Duke Energy Company is planning to construct a coal-fired steam power plant in China. The engineers target that the power plant can produce at least 70,000 kilowatts of the power output to meet the electricity demand. They are considering whether the simple ideal Rankine cycle or the Carnot cycle can be used to achieve the target. Suppose that the steam with a mass flow rate of 100 kg per second enters the turbine in both cases, and 5 megapascal as the saturated vapor, and condenser pressure is 50 kilopascal. So, determine the power output and the thermal efficiency of the Rankine cycle, and if the condenser acetate is a saturated liquid for Rankine cycle, draw the TS diagram. And for B part, determine the power output and the thermal efficiency of the Carnot cycle if the boiler inlet state is saturated liquid for Carnot cycle, and draw the PV diagram. Hence, state which is more suitable as the operating principle in this case. Also, state two methods to improve the efficiency of the chosen cycle. The question is almost similar to the standard question, but in this case, we need to find out which of the power output is sufficient, is more than 70,000 kilowatts. And also, in this case, the Rankine cycle we need to draw the TS diagram, but for the Carnot cycle we need to draw the PV diagram. So we solve like the question just now. We find out the hash1, hash2, hash3, and hash4. And since we need to plot the TS diagram, so we find the temperature value, and we find out that all the value hash4 and the hash1, hash2, hash3, everything. So solve like the question just now. We plot the TS diagram. And the power output, since we know the information is the mass flow rate is 100 kg per second, and the power output is actually equal to mass flow rate and the network output. And the power output will thus equal to 72,003 kilowatts. And for the Carnot cycle case, it's just like the solution we do just now, to make the same assumption that enthalpy3 and enthalpy4 will equal to that of the Rankine cycle, and the enthalpy2 and enthalpy1s will use the formula just now, we also find the same value. But this time we need to plot the PV diagram, so we need to find out the specific volume of each cases. And so we find out that the V1, V2, and V3 and V4 of the value. So use the formula just now, we find out that the V1 is actually equal to VF plus XVFG, which is equal to the value of the 0.90x, which the mixture quantity is 0.28 that we used just now. And for the V2, which is equal to the vapor state at the 5 megapascal, the liquid specific volume, which is 0.001286 meter cube per kilogram, and V3 and V4 use the formula, same formula, and we find out that 0.039448 meter cube, and V4 is 2.43 meter cube per kilogram. And the Q in, Q out, the network output, the efficiency, and we find out is the same like just now the Carnot cycle case. And the power output same is used the mass flow rate times the network output of the Carnot cycle. 100 kilogram times 556.49 kilojoule per kilogram will equal to 55,649 kilowatts. And then we plot the PV diagram. Since we already know that V1, V2, V3, and V4, and the pressure is always at the bottom is 50 kilopascal and 5 megapascal, so we plot this diagram, we get this value. And finally, part C, since we already know that the Rankine cycle, the power output is 72,003 kilowatt, which is bigger than the question requires 70,000 kilowatt. So that is the most suitable operating cycle. And the two methods to improve the thermal efficiency of the Rankine cycle, we can say to reduce the condenser pressure and increase the boiler temperature. Both of these methods can improve the thermal efficiency. So that's all from our group, and thanks for listening to us. We hope that you can understand more about this question. Thank you.